Welcome to another live session in the middle of the summer, just after solstice, and I hope it's cooler wherever you are than where we are today.
All right, the first question is from someone who's on with us live, Gerald, and the question is, when viewing the eclipse coming up, the Great North American Eclipse, what is the total time from start to finish and not just totality?
The total time is almost 2 hours. So totality, I think, is just under 3 minutes. So, you know, the totality is really the almost perfect occultation of the sun by the moon, and that's obviously very brief. The some part of eclipse is the time it takes for that half degree to transit completely from one side to the other. But it, you know, unless you're actually looking through a filter and seeing the bite out of the sun, by the time the eclipse is less than 30% or so, it's actually very hard to detect. The eye is a logarithmic detector which adjusts to ambient light levels. So even a slight dimming of the sun, even by 50% or so, is actually sometimes hard to detect, especially when it's changing very gradually. So it really doesn't get dramatic until just before and just after totality. So, you know, the total span of time where it's clear something is going on and it's getting dark and the temperature is going down is probably 15 minutes or so.
All right, our next question is from Adam, who asks, astronomy seems so advanced that all our major discoveries are coming from very large or in-orbit telescopes. Is there anything left to be discovered from a standard or advanced backyard telescope?
Absolutely, because there are too many interesting targets for astronomers to cover them all. So something that's pretty much true of all major big telescopes, the big ones we have, the 8-10 meter telescopes, and here and elsewhere, is that their field of view is very small. So they're looking at a chunk of the sky that's few arc minutes on a side. The largest chunk of sky, typically for a very large telescope, is about the angular size of the full moon. That's a very small fraction of the sky. So these telescopes are looking deep and they're looking narrow. Now, there are a handful of telescopes designed for survey work. The Large Synoptic Survey Telescope being built in Chile with one of our mirrors is a prime example of that, designed to look at the whole sky and survey the whole sky. But for the most part, astronomers are homing in on very distant targets, very faint targets in small fields of view. So the opportunity that leaves is for people in two aspects. It leaves the opportunity for people to study the behavior of objects where there simply aren't enough large telescopes or even astronomers to follow them all in detail. And second, of course, it leaves open that time domain of looking for variability or behaviors that may take months or years to occur, where patience is required, but a lot of photons are not. Exoplanets is the classic area of science, very exciting frontier science, where small telescopes are making a big contribution. As you recall, the first exoplanet, 51 Peg, was discovered in 1995 just using a 1 meter telescope in Geneva, not even a great observing site. And that's a pretty small sized telescope. And a lot of exoplanet science is done with telescopes of 1 meter or smaller. So if you're looking for transits or which requires patience, requires a lot of targets, requires a large amount of monitoring data, then small telescopes can make a contribution. The other area they can make a contribution is in trying to detect supernovae. So basically in every galaxy in the universe, a supernova goes off somewhere about once every 50 to 100 years. So astronomers are able to find supernovae at large distances, but actually for nearby galaxies where the supernovae would be bright and easy to detect in a, say, 8 or 10 inch telescope, astronomers are not staring at these galaxies looking for supernovae to go off. So there are amateur networks that are observing dozens or hundreds of nearby galaxies trying to detect supernovae. There's also solar system science that can be done with modest-sized telescopes. And there are about 50 different kinds of variable stars, for some of which the physics is not still completely understood, and many of the prototype objects are certainly detectable with small telescopes. So in total, actually, there's a ton of work that can be done with a small telescope, especially with a CCD at the back end, which makes it very sensitive.
All right, the next question is from Alex, who is on with us live, who asks, what are some of the most exciting things and developments that you expect to see in astronomy over the next few years?
I think the exciting developments in astronomy, I mean, exoplanets are still a very rapidly moving field, and so we can anticipate that the progress on Earth-like planets will reach the point where we can start to sniff with spectroscopy the atmospheres of Earth-like planets to try and see potential evidence for biology altering those atmospheres. That would be a dramatic, profound discovery, and it could happen in the next few years. One of the most exciting missions in the next few years is the James Webb Space Telescope, due to launch in October of next year, so just over a year away. And that telescope, 6.5 meters, far red part of the optical spectrum and near infrared optimized, is going to look for first light in the universe. It's going to do some exoplanet science, look at distant galaxies. It's going to almost certainly in its first year or so find things that could not be found with Hubble or any other existing telescope. Also, we should see first light on the first couple of the next generation of super large telescopes, the 20 to 30 meter telescopes, bigger than anything we have now. And again, because they can see objects that simply couldn't be detected with existing telescopes or gather a lot of information on targets that can be detected, they're going to almost certainly find brand new things. There are also discoveries going to be made in gravity waves. Remember, as of now, we only have 3 solid confirmations and 1 potential confirmation of gravitational wave from the first LIGO runs. As LIGO continues to accumulate data, it's likely that the gravity wave detections will come at a rate of about 1 a month. So within a few years, we could have dozens of gravity wave black hole merger type events to study. And that's going to transform that science from the sort of gee whiz of the first discovery to a real systematic understanding of black holes and how they merge, and also testing relativity in new ways. So there are actually plenty of things happening in the next couple of years that are going to make newspaper headlines.
So you basically answered Catalin's question, who asks, what is the future of gravitational wave astronomy? But maybe you could say more explicitly.
Sure. Gravitational wave astronomy is a brand new field of science. It's been decades in the making. The LIGO project, the first technical papers describing LIGO were written in the late 1970s, early 1980s. It was visionary work, of course, because it was very far from being funded. It was not even clear it was technically feasible. So these people, groups, especially at MIT and Caltech, that collaborated on the project, they stayed the course through some very difficult times, and also some times where funding was not there in the level they needed, because this project has cost over $1 billion as we speak. So gravity wave science is brand new, and as we start to detect more than a handful of events, which is all we have now, people are going to start to understand much better the population of black holes and how they behave when they merge. One of the initial surprises has been that the black holes in the LIGO events are massive. They're 30 to 40 times the mass of the sun, and normal theory of stellar collapse really doesn't predict many black holes that massive. The significant point being that LIGO could have detected lower mass black holes, say 10, 12 times the mass of the sun, yet the first detections have all been more massive than expected. So we're faced with issues of not maybe understanding fully how black holes form from massive star collapse. Obviously, the testing of general relativity occurs each time there's one of these merger events. And this is testing general relativity in ways where it's never been tested before in the strong gravitational regime. So we can expect the LIGO science to mature. Now, these are the first known events, but there are other type of events LIGO can detect. It can detect certain types of supernovae where the collapse is asymmetric and gravity waves are emitted. It can detect neutron star coalescences or neutron stars and black holes merging, in which case we learn about neutron stars and how they're put together, as well as black holes. And then there's the possibility that LIGO could detect signatures from the early universe. That's much more speculative because theory does not cleanly predict what the early Big Bang gravitational wave signature might be. But there are certainly people that are trying to predict that, trying to make theories of it, and trying to see if LIGO can detect it. So LIGO will mature rapidly in the next few years and keep all of those hundreds of scientists that work on it pretty busy.
All right, our next question is from one of our live viewers again, who asks us, the Kepler catalog was just released by NASA. What new information does this provide astronomers?
So the Kepler catalog release, to astronomers who work in this field, the catalog release doesn't actually tell them anything new because they've been working with Kepler data for a while. When astronomers release a catalog, whether from a space telescope or a ground-based telescope, the act of putting together a catalog means that the objects go through some rigorous screening to make sure that they're real. One of the issues with Kepler is that it only assigns a probability that an event is actually an eclipse, as opposed to noise or some stellar phenomena, maybe not well understood. So Kepler is always just assigned a probability that each of its transits are real. To be in the catalog, the probability has a very high degree of confidence. So this catalog is essentially the gold-plated Kepler objects. So it's just over 4,000, I think. And there may be a total of 5,000 Kepler exoplanets in their sort of working catalog. So the catalog itself doesn't contain anything brand new for most of the astronomers who are working on Kepler data. And those astronomers, of course, are trying to push Kepler to the limit. They're trying to detect lower mass or lower size planets, say things smaller than Earth size, down to Mars size, which is right on the edge of what Kepler can do. So they're pushing the data. And those detections, of course, involve detections that are not 100% guaranteed. And so at the edge of the research, of course, you're always pushing well beyond the catalog bounds. Another thing people are using Kepler data for, which has never been detected, is to detect an exomoon. Most people are probably aware of the James Cameron movie, Avatar, which is about life on an exomoon, a moon of a giant planet. And we do, within the solar system, believe there are moons of giant planets with conditions for life. No exomoon has ever been detected, which is to say the moon around a giant planet in another star system. It's right on the edge of what you might be able to do with Kepler data. And there's at least 3, maybe 4 groups actively working on that. Again, that's not anything that's been published, and people making those detections are working absolutely at the limit of Kepler data, where they won't be 100% sure, even if they claim a detection.
All right, the next one is from a live viewer named Jihan, who says, hello from Botswana. How long do you expect the Hubble Space Telescope to continue to function?
Hello, good to have someone from Botswana. I've been to Botswana about 8 or 9 years ago, visiting a friend in South Africa, and we drove to Botswana and had a nice little field trip. Hubble Space Telescope is still in routine operation. It's a venerable facility, in its 3rd decade, approaching the end of its 3rd decade. But it's on its 4th or 5th set of instruments, so each of the servicing missions has rejuvenated its capability. It's still only a 2.4 meter telescope, a fairly small telescope in terms of world rankings, sort of just about in the top 50. But these instruments that it has are essentially state-of-the-art. They're teams vied to build the instruments. They're given that you have to be well in the pipeline to be space rated. The technologies are not completely state-of-the-art because they have to be locked down for space flight testing years before the actual launch. But Hubble instruments are exceptional, and so Hubble is still competitive. The oversubscription, which is to say the number of proposals put in relative to those that can get time on the telescope, is 6 or 7 to 1 every cycle, which is a very high rejection rate. 80–85% are rejected, and those are good proposals. I've been on those panels several times. So Hubble is still very competitive. There's a practical and a funding issue, which is that the budget that funds NASA, and especially these telescopes in space, is the same budget funding JWST. So NASA and the Space Telescope Science Institute in Baltimore, that operates the Space Telescope, is forced to shrink its number of staff and scientists associated with Hubble to ramp up James Webb work. And that's going to put a limit on what kind of Hubble science can be supported. Hubble is not ever going to be serviced again. So basically, Hubble's demise will almost certainly come when it loses gyros so as to be unable to point accurately in the sky. And then it'll essentially be sort of dead in the water, if you like. There is a plan, which is somewhat controversial, to deorbit Hubble and bring it back down. That's very expensive, much more expensive than, of course, letting it fall into the atmosphere in a safe part of the Earth's surface and just break up as the heat sort of pulverizes it into small pieces. So Hubble will die at some point because no one's going to go up to fix the gyros or solar panels if they fail, or add new instruments. But that's probably 3, 4, maybe even 5 years away.
All right, the next question is from another live viewer named Kim, who asks, I'm finishing up a bachelor's degree in physics. Are there jobs out there in astronomy for someone who does not have a master's degree? What advice would you have, if so or if not?
Well, physics is, of course, a great first degree, and most astronomers, most professional astronomers, have physics as their first degree. I did, studying in the UK. So you've got a good qualification, of course, that makes you employable in various sectors, in academia, but also industry, and even in the tech sector or the IT sector. There are jobs in astronomy or doing astronomy for people without advanced degrees in astronomy, but they're not typically research jobs, and they're not typically standard type jobs in universities. So universities are fairly hierarchical. So the path professionally for an academic astronomer is the bachelor's degree in physics or related field, a PhD in astronomy, or could be in physics with a specialty in astrophysics, and then a postdoc, time as a research scientist, and then potentially a faculty position or a staff position at a major observatory. Now, all the major observatories in the world, the big ones, hire people who do not have advanced degrees in astronomy, but know a lot of astronomy, especially people with hands-on skills. And those jobs are quite varied. Obviously, there are jobs as telescope operators. There are jobs as instrument support scientists, although you have to go through some training to be in a role like that. There are various technical support jobs associated with testing instruments or site testing, or working on the telescopes themselves, refurbishing them or upgrading them. A lot of big and expensive and delicate hardware involved in any major observatory, and people with technical skills are required to do that. So I would say there are a number of jobs in astronomy, real astronomy, for people without advanced degrees, but in some of those jobs you'll reach a sort of a glass ceiling of advancement without an advanced degree.
All right, the next question is from one of our live viewers who asks, in your view, will it ever be possible to harness gravity?
Well, in the sense of manipulating gravity, that's an interesting question, and I suspect not. Ever, of course, is a long time, but so I'll just say within the foreseeable future. We have a good understanding of gravity. We have a good theory of gravity. The general theory of relativity passed all its tests so far and is now, with gravity waves, being tested in the strong field regime. So it's a very successful theory. That theory itself is based on curved space-time, of space-time, a hyphenated four-dimensional entity being altered by mass energy, another hyphenated entity in physics, associated with it. That the fact that space-time is curved by mass energy does not necessarily suggest a way of harnessing gravity. Obviously, if we could manipulate mass and energy in some significant way, we could implicitly and explicitly alter the gravity associated with that mass energy. We know how to convert mass into energy and vice versa, but really in quite limited ways. Fission and fusion are the two most obvious ways we do it. We do it in small scale in the lab and not really on large scale with large objects. So our abilities to alter gravity are extremely limited because of that, just because of the difficulty of an experiment that changes a mass energy configuration substantially, which is what would be required to change the gravity substantially. So at this point, we are nowhere near technology that can harness that. In the sense of gaining control of gravity. And certainly extending that idea, we don't have any way of countering gravity, the idea of an anti-gravity or switching off gravity at will for our own purposes. That's science fiction at the moment and may just stay science fiction.
All right, the next question is from Adrian, who is on with us live, who asks, how will the James Webb Telescope turn around and position itself to observe certain objects?
So the James Webb Space Telescope is sitting at a Lagrange point, a balance point in gravity between the Sun, Moon, and Earth at about 1.5 million kilometers or 1 million miles from the Earth, in an unserviceable location, which means astronauts can't go there to fix it. It's deployed remotely and controlled remotely from the Earth. Like all telescopes, it's built around a stabilized gyroscopic system, which allows it to point to particular regions in the sky. So like a ground-based telescope or any space-based telescope, the James Webb will go through it in its startup phase with a set of pointing tests that will lock the gyroscopes and small sightline telescopes onto celestial targets and calibrate the way the telescope points and where it's pointing in the sky. And thereafterwards, it uses its gyroscopes and then reaction wheels to move the telescope around the sky. So James Webb is not limited in where it can point, with the exception, of course, that it, for safety reasons and protecting the detectors behind the telescope, it's not allowed to point anywhere near the Sun. It's also not allowed to point anywhere near the Earth, because the Earth is an extremely bright target that would saturate, if not burn or destroy, its detectors. Hubble Space Telescope has the same limitation. For Hubble, that limitation is much more severe because Hubble's in an Earth orbit, a few hundred miles above the Earth, so the Earth takes up a big part of its potential sight line. At the much greater distance of James Webb, the Earth is a small target and fairly easy to avoid. The Sun is a small target too and easy to avoid, but otherwise James Webb has free reign. And what really counts is how you take all the observations people plan and minimize the amount of time and, by implication, fuel or energy, solar energy in this case from solar panels, is required to move the telescope around the sky and do its science. So the projects that people submit with different targets in different parts of the sky are not usually done continuously. Usually the telescope targets for different programs are sliced up into regions of the sky so that the telescope can do its work most efficiently, moving the least amount on the sky, because that takes time.
Right, the next question is from Julian, who is on with us live, who asks, how busy is the Mirror Lab here at the University of Arizona?
The Mirror Lab is luckily busy. It would be bad if it wasn't. It wouldn't mean we didn't have business or contracts or work for all those clever scientists and engineers. The Mirror Lab, for people who don't know, is a mirror-making facility under the football stadium at the University of Arizona. It's the place where Roger Angel, starting in the late 1970s, started to imagine how to make mirrors faster, meaning bringing their focus to a point at a small f ratio, not far above the mirror itself, and lighter, meaning that the telescope that holds the mirror can be lighter, move faster in the sky, and be cheaper to construct. It's been stunningly successful. Angel's worked his way up from 2-meter mirrors in the early 1980s up to the 8.4-meter mirrors that the Mirror Lab creates now. The Mirror Lab is always busy because their staff is limited, and so the two main tasks in the Mirror Lab are assembling the materials to make a mirror, going through the heat cycle to melt those materials, spin casting a mirror and letting it cool, which takes months. And then the second task is taking that mirror out and polishing it to the spec, which gives super sharp images. Those are sort of different processes that take part in different parts of the Mirror Lab. The same people have to work on both. So at the moment, it's not possible. There's usually one mirror that's about to be cast or has just been cast, and another mirror, the previous one, that's being polished. So the staff can do that. The Mirror Lab actually has enough projects and work that if they built a second oven, they could actually, increase the pace of the work. For example, we have to make 7 mirrors for our Giant Magellan Telescope. We're on the 4th right now, and the pacing of that project, a mirror completed every 18 or so months, means that we're 5 or 6 years away from finishing all the mirrors for that telescope. And we'd love that to be quicker, which would require a second oven. It would also require extra staff to do 2 mirrors in parallel. So at the moment, it's one staff, and that staff has to share their time between polishing one mirror and casting the next mirror. And that keeps them pretty busy. So I would say the Mirror Lab is running pretty much at full capacity right now. Every now and then, if there's a slack in the schedule, the Mirror Lab, which generally casts mirrors for major corporations, major telescope-based corporations or university consortia, does actually take a contract from the military. The Air Force, in particular, have a strong demand for lightweight, large, fast optics telescopes for tracking satellites, and so the Mirror Lab has taken Air Force contracts in the past, and so it can, if there's a gap in the schedule, it's able to do that.
Right, our next question is from Kushal, who's on with us live, who asks, as matter and antimatter annihilate, they form virtual particles. Can you please explain how that works?
So matter and antimatter annihilating actually produce, well, they produce photons, so they don't really produce particles. So you've got particles and antiparticles, which when they come together, annihilate to create pure radiation, gamma rays essentially. Even the lightest particles like electrons, each electron has a half an MeV, or 500,000 electron volts of energy. And so when an electron and a positron with the same amount of energy come together, they create gamma ray photons. So particles and antiparticles coming together will create pure energy. But what I think the question's alluding to is a different phenomenon in physics, where out of the vacuum itself, there's a possibility for particle-antiparticle pairs to come briefly into existence and then disappear again. If you can imagine the energy form of the Heisenberg uncertainty principle, Heisenberg uncertainty principle says the uncertainty and the momentum of a particle times the uncertainty in the position of a particle is equal to the Planck constant divided by 2 pi. There's an analogous form of the Heisenberg equation that says that the uncertainty in the energy of a particle times the uncertainty in the time of its state is also equal to the Planck constant divided by 2 pi. And so that Heisenberg formulation opens up the possibility of particles coming in and out of existence as pure energy, if they do so for a short enough time. Now, since there's another conservation principle in operation, which is the conservation of baryon number or particle number, particles have to appear and disappear out of vacuum or energy with an equal and opposite antiparticle. So the virtual pairs are essentially almost evanescent particle-antiparticle pairs that come in and out of existence on extremely short times. I mean, we're talking about less than picoseconds, femtoseconds, 10 to the minus 15 seconds, if it were electron and positron. It sounds very esoteric, but the effect, the implicit pressure of this evanescent particle-antiparticle pair, that's been detected in the lab decades ago, actually. So it is virtually certain that these particle-antiparticle pairs do actually exist. And so we can create these pairs out of essentially pure vacuum.
All right, the next question is from Dominique from Montreal, who asks, with all the new planetary discoveries from the Kepler telescope, do you think that money will be invested into even more powerful telescopes, something beyond our current tech? And I just wanted to have you clarify, they mentioned the TRAPPIST planets, but those were not discovered by Kepler, so just we should clarify that.
Right. So the Kepler has given us the lion's share of the exoplanets we know, but there are a number of other projects that are underway. And the limitation of Kepler, it's done incredible work, but its limitation, it was staring at one patch of sky, 160 square degree patch of sky, over and over again for 5 years, essentially, to find the exoplanets in that region. Astronomers are very much interested in finding the nearest Earth-like exoplanets, or all exoplanets, at much shorter distances. So most Kepler planets are hundreds, even thousands of light years away. It's going to take different facilities to find the nearby Earth-like planets. TRAPPIST system is one example. Those planets are a few dozen light years away, as I recall. Their planets have been found around the Proxima Centauri system, the nearest star system to the Earth. So It is small telescopes, not Kepler, but ground-based telescopes, and even arrays of those telescopes that are contributing to these very important, fairly bright nearby planets that Kepler couldn't find. But there are other missions underway. NASA is obviously very interested in characterizing life around on these planets, potential life on these Earth-like planets, and Kepler is only designed to detect them. It can't do life characterization or detect biosignatures. So NASA has a couple of missions in the pipeline that are all 5 to 10 years off and need some serious funding at the level of a few $billions each to try and characterize life on Earth-like planets, including some that Kepler found. Meanwhile, ground-based exoplanet research is doing extremely well with small telescope arrays looking at these more nearby targets.
All right, so we've had several people comment that they're interested in the phenomena of quantum entanglement. Some people would like to just understand what it means, and then other people would like to know when, if you could use this as a way of communicating immediately with a space probe that's very far away.
Mm-hmm. So quantum entanglement is a phenomenon out of physics that it's been predicted for over half a century. The experimental ability to demonstrate entanglement has happened only in the last couple of decades. It has started with very elegant experiments by Alain Aspect, a French physicist, in the late 1970s into the 1980s, and now it's got quite sophisticated. The principle is fairly simple. You can have, remembering that light can operate as a wave or as a particle, you can create what are called split photon experiments, where you send light and you can reduce the intensity of light till there's one photon at a time traveling through your instrument through a half silvered mirror, where if you had a beam of light, half of the light was going in one direction and half being deflected in another direction, and then you could combine that light at the end of the instrument to detect it. Well, as you take this down to the level of one photon, you actually create a coherent state where the photon seemingly travels along both paths through the instrument simultaneously. And the fact that it does is called entanglement. The photon is entangled through the two path lengths, and the paths can be separated by meters. And you can show that it's entangled because if you do something to destroy one of the path lengths, the information on the other path length is destroyed as well, instantaneously. And so there's coherent information, coupled information being held of two different paths of a single photon. And so that is entanglement, almost the definition of it. Now that's the original demonstration, and since then there have been various ingenious ways of demonstrating entanglement, including in the lab, but most excitingly over large large distances. So in the last few years, much bigger versions of the lab tabletop experiment have shown that coherence or entanglement can occur for photons that are traveling transatlantic or intercontinental distances. And there's even been one experiment in the last couple of years that tried it between orbit and the Earth. Well, that's only a few hundred miles. So actually some of the terrestrial experiments, the distance was a few thousand miles. That opens up the possibility of having coherent information where the information is held at widely different locations. And the question is, how different could those locations be? Could it be across the solar system, across the galaxy? Well, as a practical matter, you can't really do those experiments because the galaxy is 100,000 light years across. So we can't really set up that kind of an experiment. But in the experiment so far, there's no limit to the amount of distance over which entanglement phenomena can be demonstrated, which is very exciting. Now that's these are technical tour de forces to do these experiments. The practical application really is coming in another direction. It's coming from the idea that entangled information in a quantum system is actually a very efficient way of packing information. The information, of course, is probabilistic. It's not as simple as ones and zeros, binary on, off. But quite complex information can be coded in an entangled system. And so people are trying to build up a significant number of particles or waves where the entanglement can be demonstrated as a way of coding and recovering information, and therefore improving the limits of fundamental computing. These are called quantum computers. And the very simple rudiments of a quantum computer have been demonstrated in the lab. But there's nothing like, I would say, a practical application of a quantum computer that would rival something we have for more conventional technology yet.
The next question is from Art, who is on with us live, who asks, to date, how far away is the furthest object or event we have ever observed?
So really the furthest observation event that's routinely observed is the microwave background radiation. That radiation emanated from the universe at a redshift of 1,000, which, and since redshift is just an expression of the stretching of wavelength of light by the expansion of space-time, that means the universe was 1,000 times smaller and 1 billion times denser than it is now. So that microwave radiation, easily observed by microwave telescopes and interferometers around the world and studied in great detail, is a very old signature of the universe. The redshift of 1,000 corresponds to a time about 400,000 years, 380,000 years actually, after the Big Bang. So in a universe that's 13.8 billion years old, here you have a signature that's only 400,000. That's less than 1 million out of those 13.8 billion years from the origin, from the Big Bang. So that is the oldest routine signature that astronomers can detect. Now that's a radiation signature of the Big Bang from the time where the universe cooled enough that stable atoms formed. If we're talking about what's the most distant object, astronomical object that's been found, there's a pretty active competition amongst certain cosmology and extragalactic research groups to find the most distant galaxy. And there's usually a little controversy because the redshifts of very faint, very distant galaxies are based on feeble amounts of light, and very big telescopes are needed to take a spectrum, and even then you're not always sure. I think the highest redshift securely measured is about 11.3, a Z of 11.3. Remember, that's to compare to a Z of 1,000 for the microwave background. And that, of course, means an object whose light was emitted when the universe was 10 or 11 times smaller than it is now. And that's an object that's seen a couple of 100 million, maybe 300 million years after the Big Bang. And that's a good fraction. It's 95% or more of the age of the universe ago. So we can see light from objects formed pretty soon after the first gravitationally collapsed objects happened in the universe.
All right. The next question is from someone on with us live who says that in part, as a result of taking this class, I've been on a team using an 18-meter radio dish using 21-centimeter hydrogen line to observe. What sees further, a visual telescope or a radio telescope like ours?
Typically, radio telescopes see further because the obscuration presented by thin medium between stars and even the thin medium between galaxies is essentially transparent to long wavelength radio waves. So 21-centimeter waves travel cleanly through the galaxy, and in fact the galaxy itself, the rotation of the galaxy, remember we're sitting in the disk of the galaxy, and if you try to look to the galactic center, it's not really visible in the northern hemisphere, but you go in the southern hemisphere and look towards Sagittarius, you cannot see the center of our galaxy. Only 1 in a billion, I think maybe even 1 in a trillion photons reaches us, visual photons reaches us from the galactic center because of the dust and obscuration through the sight line of the galaxy. But radio waves and 21-centimeter waves travel all the way out. So the galaxy was actually first mapped in the 1920s and 30s, the rotation of the Milky Way itself and the size of the galaxy, using radio waves, because that could not have been done with optical waves. So the answer is pretty clear. Radio waves are better for seeing through the universe. And as an aside, that's of course why when SETI was started in the 1950s and 60s, the search for extraterrestrial intelligence, people decided to look for artificial signals created at radio waves because those radio waves travel so easily through space. So if you were going to communicate deliberately across large distances, you would tend to use radio waves.
All right, several people have questions about time. One is, for astronomers, does time really exist? And then other people ask, can it move backwards?
So time is a slightly mysterious entity in physics. The full physics explanation of why time exists, or the arrow of time exists, is not fully in hand. These almost get to be philosophical questions. One physics question that's never been answered is time grainy? If you drill down into the spatial nature of matter and particles, you of course reach the quantum limit. You reach an indivisible units of space and particles themselves. Does the same thing happen with time, or is time smooth and continuous down to the smallest scale you can investigate? We simply don't know the answer to that. Now, space-time is posited as a connected entity of 4 dimensions in general relativity, but general relativity provides us a macroscopic description of space-time and its behavior, certainly on scale of the universe or large regions of the universe. But it doesn't really speculate as to the fundamental nature of time itself. Nor does general relativity answer the question of whether time can flow backwards, or whether there are physical regions or physical situations where the arrow of time can reverse or time can flow backwards. Now, in some forms of general relativity or some calculations in general relativity, time with a negative axis can actually exist mathematically, and we assume, physicists just assume, that doesn't correspond to anything physical, anything real in the universe, but we simply don't know. So I would say time has guarded its secrets very well.
Right. Our next question from a live participant is there a theoretical limit to the useful size of a space-based telescope?
James Webb is starting to get into the realm of the maximum size of a space-based telescope, given the technology we have now. Remember, James Webb will be 6.5 meters across, and that is too large to deploy in its normal situation of a parabolic dish. So the James Webb is made of segments which will unfold when it gets to its location. That's a very tricky procedure that makes very many people nervous about the James Webb project. So anything James Webb sized or larger will have to use a folding technology to deploy the telescope. We simply don't have launch vehicles that are big enough and can launch massive enough payloads to send huge mirrors into space, huge monolithic mirrors. Remember, the biggest mirrors that we make right here in Arizona are 8.4 meters. There is simply no launch vehicle or way to get a mirror like that into orbit. So the question then becomes, what is the largest conceivable mosaicked or unfolding space telescope you could imagine? I think if you had a lot of money, by a lot of money I mean $8 to $10 billion, which is about what James Webb has cost so far, so maybe even that's modest to do better than James Webb, you could probably go a factor of 2 or 3 larger. I think the only place where people have supposed you might get a space telescope that's larger than 10, 20, or 30 meters is on the moon. So people have wondered and dreamed about putting observatories on the moon, radio or optical, because it's a very pristine environment. So essentially it's as good as being in space. But then you have a surface, you have the possibility of an infrastructure, and so you could build, in principle, 30, 40, 100 meter optical telescopes, as big as anything you could build on Earth, by deploying them in stages and segments and putting the segments together and laser aligning them. And there are technical plans of how to do that. There's no moon base. We'd need a moon base to provide enough infrastructure to run such an observatory, and there is no moon base at the moment. No country has a moon base. But that's probably the place you'd build your biggest telescope out in space, functioning in a clean environment that's as good as a free-floating space environment.
All right, our next question is, I don't understand what is meant when people say the universe is flat. Are they talking about the galactic plane? What does this mean?
So the plane of the galaxy is flat. The universe is, the Milky Way is a flattened stellar system where the gravity has caused it to collapse along its rotation axis to form a disk. But when people talk about the universe as a whole being flat, that is all of space-time, they're talking about the geometry of space itself. So they're talking about the hypothetical experiment where if you measured triangles in space, say by shining light beams around from point A to B to C, that light would follow Pythagoras' theorem in terms of the interior angles. So space being flat means space being geometrically flat, showing no ostensible curvature. Now, you don't actually have to do a geometry experiment in space to show that space is flat. You can also use the focusing of light if space is curved. So if space is curved, either positive or negatively, it will focus, if it's positive curvature, or defocus a bundle of light rays passing through it. And nature provides us a way of testing this because we look at the light from distant galaxies or sets of galaxies, distances of space, and see if that focusing or defocusing happens. And the effect is called gravitational lensing. And so these lensing situations, of which we now know hundreds, are little miniature experiments that allow us to test the geometry of space on very large scales. And all of those experiments so far have shown that space is flat, that the three-dimensional space, the universe as at large, obeys Euclidean geometry, just conventional textbook geometry. It does not have any particular degree of curvature. It could have curvature. General relativity allows that to be the case. It is a curved space-time theory of gravity, but the universe we live in does not show any such curvature. And so astronomers or cosmologists sort of invert this logic, and they say that the flatness of space-time, when it didn't have to be flat in the theory, is now something that we must explain in terms of our cosmological model. So the Big Bang explanation for the birth and evolution of the universe has to have built into it an explanation for why space is flat. And in practice, that comes from the inflationary aspect of the model.
All right, our next question is Southern Africa a suitable location for land-based telescopes, and are there already any located in this region?
Yeah, South Africa is a very good place for astronomy and has a strong history of astronomy. I've been there a couple of times. Astronomy started in South Africa, optical astronomy, over 200 years ago, I think. The observatory of the Cape of Good Hope, on the southern tip of South Africa, was put there by the British in colonial times and has been operating. So astronomy has been going on in South Africa, optical astronomy, for 2 centuries. And it has a tradition of astronomy now. There's a South African Astronomical Observatory, which has its offices in Cape Town, but has its observatory in what's called the Karoo, the high desert near Sutherland, just up north of the northern part of the Cape Province. And so that's a pretty dark site, pretty far from any cities, and there are modest-sized telescopes, and there's also the SALT, the South African Large Telescope, which is an 8-meter telescope, which is a twin of the telescope, the Hobby-Eberly telescope in Texas. So South Africa has a very large optical telescope. South Africa is also one of the 2 homes for the next largest radio telescope project, the Square Kilometer Array, SKA. That's a hugely ambitious project to increase the sensitivity of a radio interferometer by 2 orders of magnitude. And it's based on having hundreds of dishes spread over continental scales. Now, there was a bitter competition, a very bitter and intense rivalry to get the site of that telescope because it's a $1 billion project. And in the end, they finessed the solution because the 2 top competitors were Australia and South Africa. And so in the end, they both got the project and they'll each have dishes. In South Africa, that interferometer and those radio dishes will actually extend across 4 countries. I think they're from South Africa, they're Botswana, Namibia, and I'm going to forget the 4th country, but a large part of the southern part of Africa. So South Africa is definitely an astronomical center now, and it's always been important. It samples the southern sky in a way that otherwise is only possible in Chile and Australia.
Right, so our last 2 questions, we're going to end on a more philosophical bent, and they're sort of related. What are your thoughts about the concepts in the question, is the universe conscious, And another person says, I think that stars, galaxies, and other astronomical objects should be considered to be alive. What do you think?
So I'll deal with the living aspect first. The question, it's a scientific question and a philosophical one. Do we live in a biological universe? It's a profound one, and one we actually hope to start answering in the next decade or so. The most conventional way of framing that is to imagine that the universe contains many sites where biology could exist beyond the Earth itself, and that there are going to be similar locations, Earth-like planets, or perhaps moons of giant planets scattered around the stars that almost all seem to have planets around them. That's a more conventional framing of life in the universe, and at that level, the universe could indeed be biological if biology is widespread through our galaxy and other galaxies. The question of whether there is either biology or consciousness on even larger scales than the organisms of this planet is of course very speculative and sort of beyond the realm of conventional science. So biology is a very particular thing. It's based on the chemistry of carbon. It's based on replicating molecules which hold information, DNA and RNA, and it's based on the compartmentalization of that information in small entities called cells. And then you can build larger and larger packages from those component parts of cells, and eventually, in the history of the Earth, some of those packages of cells became sentient and conscious. We don't know how many species. We'll say it's us for sure, and maybe a handful of other species that are conscious. The question of whether this has happened elsewhere, or more speculatively, as the question implies, whether you can have larger scale versions of biology and consciousness where the individual entities, the component parts, are larger than cells or even larger than individual organisms, is completely unknown. So I'm not going to shoot it down and pour cold water on it necessarily, because I simply think we don't know enough about biology and how strange biology could be, and what the different possible architectures of biology or consciousness might be. I will say that at the moment, there's no evidence that the universe as a whole is conscious or alive. But given our ignorance of biology in the general sense, we should probably keep a somewhat open mind about that. So thanks for your questions. Great questions as always, including the philosophical ones, and we'll be back with you in a couple of weeks.